Hi, everyone. So in lecture 8, we're going to talk about some more exotic forms of looping and taking lists and looping over them into new and interesting objects. So this comes up frequently in special applications. For example, if you're trying to track what happens to a function if you take it applied to the same point over and over again. So that's called iteration, very common thing to want to do. And we might also see it sometimes when we have a list of data and we want to slowly use that data step by step to create a new object out of it. And the functions that we're going to talk about today are going to be nest and fold, a little bit of inner and outer, and then there's a specific example from this week's lesson that I would like to take the time to walk through because the way it's presented in the book I think is a little strange, and I want to show you what my approach to the question would be, which I think is more readable than what the book's presentation is, and which hopefully you'll get some insight into how I would approach a problem like that. So the first function I want to talk about is the function nest. And what nest does is allow you to perform repeated composition of functions, as opposed to the more general way that a loop is structured, where every time you iterate, you go through the entire body again. Nest specifically takes in a function as input and then a starting point, and then it will wrap that function into its own output over and over again until you reach some sort of end condition. And there's a lot of variants of nest that allow you to do different things. The most basic form of the function is just the command nest. And so the nest command itself takes in a function that you're going to reply over and over again, an input value that starts the whole chain, which is just one value, and then the number of times that you would like that function to repeat itself. So for example, if you nested the function log on an input x and you repeat that 5 times, you can see that you have the x that this was applied to, and then 5 applications of the log inside of themselves. As another example here, you might have something like you could nest squaring a function, and you could apply that to the number 2, and maybe you want to do that 3 times, which is perhaps the least efficient way of producing 256 I can think of. So what has this function done? Well, it take 2 and squared it, and then that turned into a 4, so it squared that and gave a 16, and then it took the 16 and it squared that and gave the 256. Now, we might not want to know just what the output is, but everything that was performed, every calculation that was performed along the way as well. Oftentimes when we're studying things that are iterated, we actually want to see how whatever we're studying evolved over the course of the repeated compositions. So that's performed with a command called nest list. So what nest list does is it does the same thing that nest does. It performs repeated composition, but it also keeps track of the results of every composition along the way. So the first thing it will tell you is what the original input was, and then the results in a list of every single composition that you did. So if we put nest list onto our previous examples, if we nest list this logarithm on x and we do that 5 times, it tells us in the output that we have the x that we started with, and then all of the repeated applications of log in a row. We can do the same thing with our example with the squaring, repeated squaring, by looking at the nest list of squaring a function, or squaring a number, applying it to 2 and doing it 3 times. We can see exactly what's happened here. We started with a seed of 2, it got squared, and that got squared. Now, it could be the case that I don't want to specify the number of compositions. I would like an operation to run until we meet some sort of end condition. This idea will be used in a couple of places in the homework. And one of the ways to impose an ending condition is to use the command nest while and its friend nest while list. And what nest while does is the same thing that we do with nest, but instead of specifying the number of iterations to run, I have to put some sort of Boolean condition in as a check on when this loop stops. So in this case, you can think of it as being a variant of a while loop. This is why while is in here. That this loop will run repeatedly composing this function until it meets some sort of condition check. So this code that I've written right here, what does it do? Well, we have the most command, and we already know what most does. If I took the most of a set, well, it throws away the last element. So what is this nest while doing? It takes the original set that I've built in here, A, B, C, D, E, and it applies most to it, and it continues applying most to this until it gets to the condition that the object, that is the output of the previous step, is the empty set. Because while the output of the function is not the empty set, the loop continues to run. So we can actually see exactly what's going on here, but not by using nest while, but by nest list while. Nest while list. And you can actually see what this function is doing. It starts with the initial seed, and then it applies most over and over and over again until it gets to the empty set, and then it quits because that's what we've imposed as our quitting condition. So these quitting conditions are useful when you have a specified structural operation that you're trying to do on some object, and you would like it to quit once it meets whatever the criteria happens to be. Another variant of an endpoint condition checking iterative process is a command called fixed point list. And what fixed point list does is it looks for repetition in the outputs, and as soon as the output list starts to repeat itself, then what the fixed point list command does is say, that's a fixed point, which means this process has stabilized, and now I'm going to exit. So we can look at this behavior if we looked at something like, let's take a number and we'll divide it by 2, and then we'll round down to the closest integer. So if I do fixed point list and say, this is the rounding command, is floor. So if I floor a number divided by 2, and let's give the fixed point list something to start with, like 983, and we run this, then you can see what happens here is that fixed point list runs this command repeatedly by dividing by 2 and then rounding down. And then once it gets to the point where it spits out a 0, as soon as it sees a second 0, then it quits, because repeated application of 0 means that it will never be anything other than 0, right? If you've already produced a 0 and then that 0 produced an extra 0, fixed point list says that will continue on indefinitely, and so the list has stabilized, and so I quit. So this is very useful in certain numerical computations when you know that there's some sort of convergence happening, and so these lists do stabilize. This is a good way of approaching the problem about the Capricar routine at the end of the chapter. Although you can also use all these nest while lists and various other commands of producing lists of compositions as well. So now we're going to talk about the fold command. And you should think about fold as an operation not that repeatedly applies a function to an input, but an operation that takes a function and repeatedly feeds inputs into it. So this isn't an operation on one input, it's an operation on a list. And so this will be easiest to show if I show you some examples of how fold works. If we fold f, so let's just fold some function f, and we'll fold f onto some input. So there's the initial input x, and then I have to also feed it some parameters a, b, and c. And you run that. Now this output might look a little strange here. It's actually easier to interpret what's happening if we do fold list instead, so we can keep track of how this composition is working. But what you should think is, what fold does is it allows you to fold these extra parameters into f as f runs. So f is sort of acting like it does in nest. That is to say, f is repeatedly being applied to itself, but then we have these extra parameters that are being pulled in at every stage. So it's a way of bringing in variations in the inputs as I do this repeated composition. So let's actually look at fold list of this same command, and we'll see what this is doing. So if we copy this and we paste it, and instead we write fold list, well, what actually happened here? First, we have the seed x. Then f was applied to it, but with this extra input a that's been pulled in. Now the output of that's the new thing that f got applied to, which is why this is sitting in the x slot. But then we also have this extra parameter b that got pulled in. Again, the third time, this is now the output. F of x of a and b was the output from the previous step. That has been folded in to f, but now with this extra parameter c that's come from the parameter list. And so the idea here is that sometimes when you're doing these repeated compositions, you would like to have an extra set of parameters that you can pull in at each step along the way. So this is a sort of a subtle command, but it's one with some pretty interesting applications. One thing it's really good for is producing repeated sums. So you could do something like fold with the plus command, starting with the number 0, I don't know, 1, 2, and 3. So what did that do? Well, let's take a look. So following the logic from the previous step, what has happened here is that the seed number was the 0. So that started right here. Then what did fold do? It applied plus to 0 and 1 and then stored that output, which is 1. Then what happens is it takes that output and uses it as the new input for plus. So it takes the plus and the 1 from this part of the list, but then it folds in the 2 from the fold in list, the extra parameters. And that gets us 3. Then we apply again. So another composition with plus, but now we're going to take that 3 that we produced on the previous step and we're going to bring in this 3 as the new input. So you should think of fold as being something that works on commands with multiple inputs, where we want to repeatedly apply F, but we have to provide what the second input should be as we proceed down the chain. Now, the problem I want to talk about, and a problem I think is done incredibly incomprehensibly in the textbook, is problem 7.15. So let's look at problem 7.15, and maybe not in yellow. I found the description of problem 7.15 to be sort of absurdly obscure. And in fact, if you read it, you can go down to the bottom and he actually asks, is there a better way to do this? And the code I find kind of incomprehensible. I mean, I understand what it's doing, but it wouldn't occur to me to use a bunch of substitution rules that you guys don't know yet. So we don't learn substitution and pattern matching until next chapter. And so these solutions I don't think are appropriate to the methods of this chapter. And so I want to talk about what my approach would be. How would you attack a question like this? So the question asks the following. Given a set 1, 2, 3, 4, can you find some combination of pluses and minuses so that the following equation holds? 1 squared plus or minus 2 squared plus or minus 3 squared plus or minus 4 squared is equal to 0. Is that possible? I'm actually not sure why it's rendering like this, but Mathematica for you. Okay, so the idea is, could I find some combination of these pluses or minuses that will make this work? And like I said, the approach in the book involves writing this down and doing a bunch of substitutions symbolically and then just plugging the numbers in. And I thought that I would like to do this directly. And so what I see when I look at this is the following. So I see that this is a question built off of the range of 4. And not just the range of 4, but the range of 4 squared. Now, somehow we need to inject the pluses and minuses between all of the, before the 4, before the 9, before the 16. And then we need to somehow check every single one of those things to see if we get the pluses and minuses in there in some combination, does it sum to 0? Well, the summing to 0 part is easy because I could just do a head change. So in fact, I could look at this right now and say, well, it's not going to hold for the pluses because I could do this. I could head change into a plus. That's clearly not equal to 0. So how do I get... In fact, we can go even further. No happy faces here. Is that equal to 0? No, of course not. So now the question is, how can we get into this range command? How can we get the pluses or minuses that we're interested in? What I thought when I look at this question is that we should be trying to generate a list, say, of 1s and negative 1s. Because if I could multiply my way down the chain by combinations of 1 and minus 1, then when I apply the plus head change, that will incorporate those negative signs. So how can we do that? So I can think of two different ways to generate lists of pluses and minuses. Notice in the setup for the question here that there's no plus or minus in front of the 1. So the very first thing that we need to do is generate a list of every possible combination of 3 pluses and minuses, which I'm going to take care of by using every possible combination of 3 copies of 1 and -1. I'm going to use the command tuples to do this. So if I take tuples consisting of 1 and -1 of size 3, what I'm going to get is every 3 entry long combination, every list consisting of 1s and -1s in every possible combination. And these aren't sets, because if I used sets to do this, I'm not going to get every single possible combination. So now I've got these tuples, and if I could take those tuples and I could multiply them into this list, say entry-wise, then I would have a 1 times something and a 4 times something and 9 times something. The problem is I've only got 3 entries in each of these lists. And so I need to record the fact that that 1 is always positive. And so what I'm going to do in order to make these things have length 4 is I want to make sure that I've got a 1 at the beginning. And so one way of doing that is that you can prepend, and then we want to map prepend onto our list, and we want to prepend a 1, and the thing that we're trying to map it onto, say, is this guy right here. Well, that didn't work. There we go. All right, so we prepend the 1 onto each of those lists, and now I've got entries that match up exactly with this 1, 4, 9, 16. An experiment to see how these things are going to act if I multiply them by each other. Say I just did 1, 4, 9, 16, and I just multiplied it by 1, -1, 1, -1. How does that behave? Oh, well, that's nice. We have entry-wise multiplication when I multiply 2 lists together. Okay, so if the lists are the same length, we just get entry-wise multiplication. You might think that you can multiply this list by this entire matrix, and it will do exactly that. The problem is that it will only multiply lists of the same size. So I actually need to repeat this object 8 times in order to get it inside this. So there's an easy way to do that, where I can make a table consisting of my range of 4 squared, and then I just need to repeat that 8 times. Now you'll see that this and this have the same size, right? So this right here and this right here, they have the same size now. So if I call this A, and I call this B, and I multiply those things, maybe I'll get lucky, and I'll get each entry in each list multiplied into itself entry-wise. Oh, look at that. That's nice. So now I've got a combination of every single possible plus or minus applied to all of these squares of numbers from 1 to 4. And the last step here, if I want to see what they add up to, would be to map plus inside. So I could map the head change for plus into AB. And I get all the possible sums. So what I have here is the logical core of an approach to this problem that does not involve any of these weird substitution rules that we saw in the examples that were in the textbook. You can take this logic that I've built out here and build it into something that is actually just as inefficient, because you should recognize that as the range goes up, an increase of 1 in the range, so to go from 4 to 5, takes us from 8 possible arrangements to something like, well, that's what, 16. So this is growing like 2 to the n. And so it gets very slow as the ranges start getting larger, which is why in the textbook, the ranges don't really go above like 22, for example, that they're working with. And a code based on what we've done here will also bog down in a similar way, but at least it's understandable how we did it. So the last step of this is going to be somehow construct this into a loop where it's using this logic to create the sums and then to check them all to see if there's a 0 somewhere in that list. So finally, we're going to talk about some odds and ends. And in particular, I want to talk about rule, which shows up in the last part of chapter 7. And I want to talk a little bit about how to work with rule and how it can be applied. So what is a rule? So a rule in Mathematica you can think of as a command that tells Mathematica every time you see this expression, replace it with this one. Right? That it's not an equation, and we're not saying that two things are equal to each other. You should think of it as a replacement. And so it's something that can be fed into a substitution. So in its most, this is all sort of in reference to exercise 7.8. But there are some ideas in here that are very useful, that are pointed at, that are not really explicated very well. So let's just look at what a rule is. So if I have the command rule AB, so rule AB tells me, oh look, there's this arrow, A goes to B. Well, what can I do with that? Well, suppose you had a command that looked like this. 2x plus 3y plus x a plus ya squared. And you know that you got this rule that says that every time you have an a, you can replace it with a b. How can you apply that to this expression? So we're going to talk about this in the next chapter and a little bit in the chapter that comes after that. And it was used in this chapter without being explained. But the idea is that if you actually run this command right here, which is a replace command, so this is shorthand for replace, you can feed it a rule. And it will replace, according to that rule, all of the A's with B's. Okay, so rules are very useful for creating expressions. They're implicitly used with Mathematica when it does simplification. And the idea is that, yeah, so this is all shorthand. So this is shorthand for this command, rule AB. And this is shorthand for the command replace all. Let's put this in here. And then we feed it a rule. And we get the same thing. So this is shorthand for replace all. This is shorthand for a rule. And this sort of expression substitution can be used in all kinds of ways. So for example, in our previous expression here, if I don't want to do this, but instead I want to evaluate it, I could do something like take this expression and replace a with 1 and replace b or x with 0 and replace y with 2. And it will actually replace all of these things and produce a number. Okay, so you can use substitutions to also evaluate expressions as well in special cases without defining functions. All right, so what does all this have to do with exercise 7.8? So 7.8 asks you to take a list of numbers, x1 through xk, where k is some arbitrary number, and to change that list into a sequence of rules that connect x1 to x2 and x2 to x3 and x3 to x4 and so on. So my solution to this, I think, has some very useful commands inside of it that I want to talk about. So if I was going to do this question, the first thing I would do is, how do I create a list of elements that have subscripts? So when I look at this list of x1 through xk, I would like to be able to generate that automatically. I don't have to hand code it. And one thing that's nice that Mathematica will do is it will handle symbolics when you involve subscripts. So you could table something like xi. I got down to the subscript there by hitting control underscore. And I could run I, say, from 1 to 10. Now I've got a list of symbolic elements x1 through x10. If I want to somehow make these into rules connecting x1 to x2 and x2 to x3, then I need to take this list and I need to partition it somehow, because rule only applies to elements 2 at a time. In the same way that when we were doing the graphing piece, that a really good way of doing the color there was to take the lines and break them up into individual segments. And so we're going to do that using the partition command. So if we take this and we partition it, and we partition it up into groups of size 2 with an offset of 1, well, now we're getting close, because now we've got pairs x1, x2, x2, x3, x3, x4, and so on. And so the last thing we need to do is somehow get rule inside that. So the thing about rule is that rule is a head. So rule looks at an AB at a it's not a list. It's not a function and it's not a list. Rule is a head of a sequence of objects. And so I actually need to do a head change inside this list, all these little sublists. It means that what we need to do is we need to get rule inside and as a head change. So we're going to map. That'll get us inside. This is a case where we're going to want to use the function names instead of the shorthand. So we're going to map rule inside. Let's just see what happens if we do this. Let's map rule inside to this partition right here. So there's an issue here, and the issue has to do with the fact that we're applying this to these lists, x1, x2. So x1, x2 is a list. How can I feed it into rule? You can apply rule as a head change. So we're going to take this, and if we do the same thing, but we don't apply rule, but we apply, if we don't push rule inside, but we apply it, so it's a head change, then we get the list of rules that we want, because we've head changed the list x1, x2 into a rule x1, x2. So that actually covers the odds and ends from chapter 7 that I think are interesting, and some commands that I think are really important, like the rule command and the idea of substitution that we'll talk about in the next chapter, as well as the idea of when it's important to use this map apply idea. Because if I want to push a head change into a list, I have to use map to get the head change inside, and then I have to use apply to do the head change. The shorthand notation doesn't work in most of these contexts, so you should be comfortable in either sort of formulation. All right, so with all of this, you should be able to at least grapple with the exercises in chapter 7. I know the exercises in this chapter are a little bit trickier. The programming that we're doing is getting a little bit more abstract, but I hope that you recognize at this point in the class that your facility, the ability to do different things, is greatly expanded over what it was at the very beginning, where mostly what we were doing is arithmetic computations. Okay, so I will talk to you guys soon, and take care.